Alright, so today it's day 48. I basically checked about scheduling. Okay, I can say a couple of things. For example, first one about the main intuition that how can you, okay, this is maybe not that related to scheduling, but it's how can you prove that the problem is NP complete. And it's basically you do it by reduction the problem, like creating another instance of the problem, like a simpler instance, to make it equivalent to a problem which you know it's NP hard, it's NP complete. So, and this is mostly like the 3-partition problem or the 2-partition, whatever. There are many problems that are already proved to be NP complete. So if you make an instance, you're proving that the harder problem is as hard as the easier problem. And the hard problem, it has to be a decision problem. So it has to have an answer of yes or no. That's basically it. Then I saw like something about scheduling. There is like this algorithm, which is like the Smith algorithm. There are 2 types, the SPT and WSPT, but it's really simple. Essentially, it's when we have a scheduling problem on a single machine, and we want to minimize the sum of the completion time. And the way to solve it is that you order by the processing time and schedule the tasks that take the least amount of time. And if you do it by, let's say like some tasks have like some priority, some weight, you compute like a ratio and do it by this sorted ratio. That's it. Then we have like the flow shop. We can prove that it's NP complete. Then we have like also like the branch and bound algorithm, which is like you have to compute a graph, and the graph are like lower bounds. And when you finish like the instance, you have the upper bound, and you can prune like the graph. And I also did this exercise, but it's essentially very similar. Maybe this is another algorithm, the list algorithm, which is like also giving now we have a scheduling problem, but we have many machines and we have a priority list, and we want to give like the order in which every task is going to be executed in each machine. And then here it's basically if we're going to analyze something called unstable behavior, which the definition is that even when we increase the number of tasks, the duration of each of the tasks, or the number of machines, the minimization objective still does not decrease, like even increases. So it means that, I mean, it's contrary like to the logic, because you have like more resources and you're getting like a worse behavior, and that's it. But the algorithm is pretty easy. It's just you compute like all machines are available, because you have some like precedence constraints. So the machine in here in the left hand, we say that the task 1 has to be executed before task 9. So only task 1, 2, 3, and 4 are able to be run. And then we have the priorities, right? So we can assign, if we have 3 machines, the first task, we can run them like in parallel. And once a task finished, we can schedule the next one. We delete this one. We put the next one, if there is like one that it's now available, and we push the one that is at the beginning in the priority list. That's like the algorithm. Then what is this? Another like proof and another branch and bound. That was it today.